We've worked with the imaginary numbers and we've worked with the complex numbers. So really today is day 2 of that concept. And we begin by graphing these numbers. Typically our coordinate plane, the horizontal line always represented the what? X. Vertical line, Y. Today that is changing because again, the coordinate plane was designed only for real numbers. Okay, it was not designed to include these imaginary numbers. Now the system is really nice because we have our 2 parts that make up a complex number. We have the real and then we also have the imaginary. We also have 2 axes that allow us to identify both of those. So this x is no longer x, but instead this is considered the real number. And this y-axis is now considered to be the imaginary number. Or the imaginary axis. Because again, we'd like to be able to graph these. If we start with part A, 3 plus 4i, 3 is the real, 4 is the imaginary. So the concept is still the same. 3 is positive, so 3 units to the right. And then the 4 is the imaginary, so up 4. There's point A. Negative 2, negative 3i, if we plot that one. Negative 2 to the left, down 3. If we take a look at negative 4i, do we have a real part? No. Well, we could say, yes, we do. It's 0. But now we're just going to go down 4. So we're going to stay right on that imaginary axis. And the last one, 3. There it is. Once again, for less than 69, it is no longer the coordinate plane, but we call it the complex plane. Being that we're plotting points, we can find this thing called the absolute value, which essentially, guys, is just finding the distance between that point and the origin. We want to find the absolute value of a plus bi. It is equal to the square root of a squared plus b squared. Which essentially looks like what? Pythagorean theorem. Very good. You know, if we go back to one of these that we plotted, point A, or no, let's go point B. If I want to find the absolute value, or same thing as finding the distance between the origin and that, essentially what we've done is we created that right triangle. Where this was your A value and that was your B value. Right triangle, leg squared plus leg squared over the square root. So that's where that concept comes from. Find the absolute value of the complex number. This is my A, that's my B. So the absolute value of negative 2 minus 3i is equal to the square root negative 2 squared plus negative 3 squared. You do not have to worry about that I, it's just the B value. Notice just B, not BI. Square root of 13.
I didn't get any of that. I can't see.
The other day we added and subtracted or collected like terms with the reals and the imaginary numbers. Just note we can also multiply with them. Our typical distributive property tells us we need to take negative 4i and multiply by 7. Negative 28i. Distribute to the 3i. It's also going to be minus 12i squared. And now this may be a stretch. We talked about it that day, but we didn't emphasize it a lot. What is I squared? Negative what?
1.
Yeah, very good. Good. I figured you would have remembered this one. You know, I equaling the square root of negative 1. That's good to see that you remembered I squared is also equal to negative 1. Okay, so what does that mean for us? We can go ahead and substitute that in, which means that now becomes positive 12. And we like to write the real part first, followed by the imaginary part. 12 minus 28i. And there's our form a plus or minus bi. Two binomials for part B, which indicates we got to use the FOIL process. I'll give you a head start and then I'll meet you at the end. See if you can use your rules to multiply those two. $38 plus 14i. Hopefully you came up with the same. Collecting those like terms, negative 10 and 24 gets us positive 14i. Substituting negative 1 in for I squared makes that positive 38. And then it gets really fun because not only do we have I, but now, or I squared, but now we're going to be looking at I to the 14th, I to the 37th, I to the 59th, and so forth. Okay? But there's a really cool pattern that takes place here with the i's. Okay, maybe not real cool, but at least it's a pattern anyways. If we start with I to the first, that's just simply I, correct? And if we go I to the second, we said that was equal to what? Negative 1. And if we continue to go with our exponents, I to the third, well, property of exponents tells me if I take I squared times I to the first, the sum of 2 and 1 would still give me 3, right? And I know I to the second is equal to negative 1. And I to the first is just I. Therefore, when I multiply those two together, I know that I to the third is equal to negative I. Let's do I to the fourth. Anybody know what that would be equivalent to? Yeah, good. Because we want to look at it as I squared times I squared. And what's I squared? Well, it's negative 1. So negative 1 times negative 1 is 1. Okay? And 1 is a really nice number, correct? Because it's our multiplicative identity. So now when we go to I to the 5th, instead of doing 2 or 3 or 1 and, I'm actually going to do 1 and 4. Because I know I to the 4th now is equivalent to what? 1, we just found that here. And I to the 1st is just simply I. So it's just simply I. I to the 6th, again we want to use I to the 4th. I to the 4th again is 1. So we go back to I squared, which is just negative 1. And at this point, you might be telling yourself, okay, are these things going to repeat? Yeah, they are. I to the 4th, I to the 3rd, 1 times I to the 3rd we said was negative I. So negative I to the 8th is equal to I to the 4th times I to the 4th, which is simply 1 times 1. Which again, we came up with 1. So if you notice, these things are starting to repeat themselves after a multiple of 4. Those are the same, you know, to the 6th, to the 5th, and to the 1. We could do I to the 9th, but I think you get the idea. Once again, it'll just come out to be I. So we have this rule, we have this pattern that's taking place after every 4th I. It actually starts to develop this concept called modulo, which we don't get into at the high school level, but if you take a mathematics class someday in college, good chance you'll run into that topic. But for today, what we've done is we've started to create this chart. And what we want to look at is that remainder when we divide by 4, because we said it's going to occur after every multiple of 4. When the remainder was 0, which is when we had I to the 4th, if we divide by 4, we found that it came out to be this 1 here. So this is the chart that you want for your notes. We're going to divide by 4, and then we're going to look at the remainder. If the remainder, or when the remainder is 0, then it's going to simplify down to 1. When the remainder is 1, then it's going to be I. When the remainder is 2, then it's going to be negative 1. And when the remainder is 3, then it's going to be negative I. And again, these numbers come from our list that we were able to generate up here at the top. Remainder of 0 is 1, remainder of 1 is I, remainder of 2 is negative 1. If the remainder is 3, it's negative I. Make sense? So the whole key is you are dividing by 4. If we look at 4a, I to the 30th, what number do we want to divide by again? 4. So I take my exponent and divide it by 4. And I know that 4 goes into 37 whole times. And the thing I want to look at is that remainder of 2. So I go back to my chart. The remainder is 2. And my chart tells us that if I have a remainder of 2, then that's simply negative 1. So if they give me I to the 30th, I know that's going to be equal to negative 1. Negative 2I to the 13th. Now let's just ignore that negative 2 for right now. We want to break down that I to the 13th. 13 divided by 4, 3, 12, remainder is 1. So if my remainder is 1, going back to my chart, I know that I to the 13th then will simply reduce down to just I. correct? So, negative 2i to the 13th. The negative 2 we said we'd leave alone. We substitute I in for that I to the 13th. So negative 2i to the 13th is no more than just negative 2i. Making sense? It's just taking the value on the right side of the column and plugging it in for that I to whatever power. And the last one, example number 5. Rationalizing denominators not only with radicals, but with the imaginary I. Conjugates. The conjugate of 2 plus I squared is 5. Keep the first term the same, but change the sign in between. Now the good news is our rule with conjugates still fall into place here. Do we need to do the entire FOIL process? No, because these two are conjugates of one another. So we still only need to do the F and the L. Remember that rule? Let's leave this in this form. Let's do the F and the L, the FOIL process down here. 6 times 6 is 36. Positive times negative will be negative. Square root of 5 times square root of 5 is 5. And then I times I is I squared. What's I squared equal to again? Negative 1. So negative 1 times negative 5 gets me positive 5 or plus 5. .41 is prime, therefore we know it's not going to reduce. Just so you're aware, you could write it like this too, if we distribute. If you look it up in the textbook, that's probably the answer they're going to give you because, again, dealing with a complex number, we want to be able to identify the A and the B. A, B, I. Fun, right? A through D, E, I, K, and M. Are you guys good with the graphing part of it? Let's skip A through D then. Is that helpful? Going from 8 to 4?